Have you ever stopped to wonder what actually powers a hurricane? Or even just why the wind blows at all? Well, today we're going to look under the hood of our planet. We're going to explore the invisible engine that drives literally all of our weather: atmospheric circulation. Let's get right into it.
It's one of those questions that's so simple, a kid could ask it. But the answer is this incredible story about energy, pressure, and the spin of our entire world. We feel the wind every single day. But what exactly is it that's setting all of this air in motion?
Okay, so to understand the whole system, we have to start with the absolute basics. What's the fundamental force? What's the initial spark that gets this whole engine running in the first place?
It really does all come down to the sun. See, the equator gets blasted with this direct, powerful solar energy, while the poles get these weaker, slanted rays. And that simple imbalance, that's everything. Hot air expands and gets lighter, cold air compresses and gets heavier. And right there, you've created a planet-wide variation in atmospheric pressure.
So, what exactly is atmospheric pressure?
Just imagine a column of air stretching from the top of your head all the way up to the edge of space. The weight of all that air is what's pressing down on you. At sea level, that pressure averages out to about 1,013.2 millibars. And it's the difference in that weight from place to place that's the real key.
This brings us to the two main players in this whole drama. You've got your high-pressure zones where cool, dense air is sinking and spreading out, and then you've got your low-pressure zones where warm, light air is rising up, pulling the surrounding air in to fill the space. This is exactly why weather forecasters link high pressure to clear skies. That sinking air stops clouds from forming, while low pressure means rising air, which is the perfect recipe for clouds and rain.
And here it is, the golden rule. It's that simple. Air is always trying to balance things out, so it flows from an area of high pressure to an area of low pressure. And that movement, that flow, that's what we call wind. The most important thing to remember is this: no pressure difference, no wind.
But, of course, it's not quite that simple, is it? If air just moved in a perfectly straight line from high to low, our weather maps would look totally different. There's a massive global force at play that adds a literal twist to the story. So you have to wonder, right? Why do winds curve across the map? Why do big storms spin? What's stopping all that air from just taking the most direct path from point A to point B? The answer is pretty wild. It's because we live on a giant spinning ball. Enter the Coriolis force. Now, this is a little tricky because it's not a true force that's actually pushing the wind. It's an apparent force. Think about it like this. If you're on a spinning merry-go-round and you try to roll a ball straight to your friend on the other side, the ball is going to look like it's curving. The ball is actually moving straight, but the ground underneath it is rotating. That is exactly what's happening to the wind on our spinning planet. The rules here are pretty straightforward, but they have huge consequences. In the northern hemisphere, things get bent to the right. In the southern hemisphere, they get bent to the left. But look at that last point. This is so important. The effect is zero. It's totally absent at the equator. And that is a critical piece of the puzzle. And that explains a massive meteorological fact. You can have all the warm ocean water and all the rising air you want, but if you don't have the Coriolis force to give it that initial little twist, a massive storm system like a hurricane simply cannot get organized and start spinning. No spin, no cyclone. Okay, so we've got uneven heating creating our pressure differences, and we've got the Earth's spin deflecting the wind. Now let's zoom out and see how these forces organize themselves into these massive planet-spanning patterns. Meet the Hadley cell. This thing is the powerhouse of the tropics. It's like a gigantic looping conveyor belt. Warm, moist air rises up at the equator. That's what creates all the lush tropical rainforests. It travels high up towards the poles, cools off, and then sinks back down around 30 degrees latitude. And this is why so many of the world's great deserts are found right around that 30-degree mark. It's where the atmosphere's conveyor belt is just dropping off all of its dry air. Now, the Hadley cell doesn't work alone. It's actually part of a 3-cell system in each hemisphere. You have the polar cell, which is driven by that intensely cold, sinking air at the poles, and then you have the Ferrel cell, which is kind of caught in the middle. It acts like a big gear turned by the motion of the other two. This turbulent middle zone is also where we find the jet streams, those high-speed rivers of air that shape our daily weather and even how long our flights take. All right, let's zoom back in. These huge global circulation patterns create these enormous, distinct bodies of air. But what happens when these giants run into each other? Well, that's where our day-to-day weather starts to get really interesting. We call them an air mass. It's basically just a huge bubble of air that takes on the personality of whatever surface it's been sitting over for a while. If it forms over a cold Canadian plain, it's going to become cold and dry. If it forms over the tropical Atlantic Ocean, you bet it's going to be warm and humid. And just like oil and water, these different air masses do not mix easily. When a cold, dry air mass from the north slams into a warm, moist one from the south, they form a distinct boundary. This atmospheric battleground is called a front, and it's a major trigger for clouds and precipitation. Meteorologists are always tracking 4 main types of these fronts. A cold front is an aggressive push of cold air, and it often brings these sharp, intense storms. A warm front is a bit of a gentler situation, with warm air gliding up and over the cold air, which usually causes a more steady, widespread rain. And then you have stationary and occluded fronts, and each of those creates its own unique brand of weather. So, what happens when you combine all of these ingredients, intense warmth, tons of moisture, and that critical spin in the most extreme way possible? Well, you get the weather engine's most awesome and destructive creation, the tropical cyclone. The fuel for these absolute monsters is heat. Specifically, it's something called latent heat, which gets released when massive amounts of water vapor condense into clouds. That's why they can only form over these vast stretches of really warm ocean water. They're basically acting as enormous heat engines. So what's in a name? Well, it really just depends on where in the world you are. Over in the Atlantic, we call it a hurricane. In the Western Pacific, it's a typhoon. In the Indian Ocean, it's a cyclone. And my personal favorite, over in Western Australia, they sometimes call them willy willies. Same storm, just a different name. The structure of these things is just iconic. Right in the center, you have the strangely calm eye, where air is actually sinking down. But surrounding it is the eye wall, and that is the most dangerous part of the storm, with the absolute fastest winds and heaviest rain. Then, spiraling out from there, you have the rain bands that can stretch for hundreds and hundreds of kilometers. And the power is it's staggering. The winds in the eye wall of a strong tropical cyclone can reach speeds as high as 250 kilometers per hour. That is just sheer destructive force, and it's driven by nothing more than warm water and spinning air. It's really easy to see these storms as just destructive chaos, but there's a deeper way to look at it. They are a powerful, even violent, manifestation of the atmosphere trying to balance itself. They're a crucial way for the planet to move immense amounts of heat energy from the tropics up towards the poles, allowing the whole global system to return to a more stable state. This incredible global engine is always running, always adjusting, always in motion. So the next time you look at a weather map, or you just feel the wind on your face, you'll know the immense and beautiful physics happening all around you. This engine never stops. So what do you think it'll create tomorrow?